So we're asked to show the square root of z plus 1 by the square root of z minus 1 is equal to minus the square root of z squared minus 1. Here, square roots are principal values. So notice that z plus 1 by z minus 1 is equal to z squared minus 1. Therefore, when I take square roots, everything is going to be fine up to a question of sign. So when I look at complex numbers, if I think of them as being modulus in argument form, the modulus of this side is equal to the modulus of that side. It's a question of what is the argument of this side as against the argument of that side. Notice that because of this, we know actually that the arg of root z plus 1 root z minus 1 is equal to the arg of root z squared minus 1 plus k pi, where k is an integer. If k is an even integer, it means that these arguments are the same, and that actually means that this product of square roots is equal to plus that square root there, and if k is an odd integer, it means that this product of square roots is minus that one there. Okay, so 3 cases. One is when the imaginary part of z is greater than 0, a second one is when the imaginary part of z is equal to 0, and the third one is when the imaginary part of z is less than 0. I'm just going to look at the first case, but the other 2 cases are very similar. Actually, this one is easier. So, notice real part of z is less than minus 1. Imaginary part of z is greater than 0. That means that z is somewhere in the second quadrant. If I take z plus 1, that's got the same imaginary part of z, so it's above the axis. And since the real part of z is less than minus 1, the real part of z plus 1 is less than 0. So this is also in the second quadrant, and so is z minus 1. Now, just to make notation a little bit easier, I'm going to write q1 for the first quadrant, q2 for the second quadrant, and h minus for the lower half plane. So, observe that. We're looking first of all at these things here. The z minus 1 and z plus 1 are in the second quadrant. When I take the square roots of these, their arguments, when I take the principal value of the square root, their arguments are halved, which actually means that the argument is going to be, here the argument is less than pi, so when I take the square roots, the argument is going to be less than pi by 2, and that's going to tell me that the square root of z minus 1 times the square root of z and the square root of z plus 1 are both in the first quadrant, and when I take the product of these things, well, it actually turns out that it's back in the second quadrant. One needs to be perhaps a little bit careful, but these are both have got arguments that are less than pi by 2, so when I multiply them together, the argument is less than pi, so it's certainly somewhere up here in the upper half plane. But in fact, it's in the second quadrant. On the other hand, when I take z, which is in the second quadrant, its argument is somewhere between pi by 2 and pi. When I square it, I get z squared, and its little a argument is somewhere between twice pi by 2, which is pi, and twice pi, which is 2 pi. So it's also true that z squared is in the lower half plane. Now, when I take z squared, which is in the lower half plane, so here it is down here somewhere, then z squared minus 1 is also in the lower half plane. Now, when I take the square root of a number that is in the lower half plane, I have to take its capital A arg. Its capital A arg is between 0 and minus pi, or perhaps between minus pi and 0 if you prefer. And the arg of the square root of that, well, if this has got an arg which is between minus pi and 0, then this is going to be between minus pi over 2 and 0. So actually we could say that square root of z squared minus 1 is actually in the fourth quadrant. So a little bit of thinking about what the arguments are like tells us that this one has got an argument that's negative, and it's actually not terribly negative, whereas this product here has got an argument that's positive, but not less than pi. Now, we know that these two numbers have got arguments that differ by a multiple of pi. What can that multiple of pi be? Well, if this one is here and that one is there, then the difference has got to be exactly pi. It's an odd multiple of pi. And this means that hence k is equal to 1. That's the k from back here. The argument of this is equal to the argument of that plus pi. And then when I exponentiate and I take e to the I times the argument, I get an e to the I pi. And that says hence square root of z plus 1 square root of z minus 1 is equal to minus 1.